Universe cosmologists are still in lack of clarity. Anyway, moving closer to illumination, one disclosure during a period that is the awesome, inescapable end comes from momentous disclosures by the James Webb Space Telescope, or JWST, the 1 billion time machine that just legitimately shut its generally essential year of insights plan to impression the weak infrared shimmer of the universe's earliest luminous articles. The Webb's vision wandered again into the IAL a very few hundred million years after the huge explosion, allowing it to gain more and better data about baby universes than any other office yet gathered. At this point, its passage of inestimable kid pictures has shown more bounty than most researchers hoped against hope. Recently, putative candidate frameworks in the early universe are jumping up in numbers that go against assumptions, with Modest Bunch considered to be doing this point, and that makes specialists go ballistic. As Charlotte Brickley, an astrophysicist at the School of Copenhagen, said, "We genuinely weren't guessing this in the extended lengths of time following JWST disclosures of incredibly adult early frameworks. Researchers and observers mixed to seem okay with them. Could the pack of peculiar, huge, and splendid early universes be a user? Perhaps because of deformities in the assessment of the telescope's hidden insights, if authentic, could they somehow or another be seen okay by standard cosmological models? Or perhaps were they the principal hints that the universe is more abnormal and complex than even our boldest hypotheses had any time expected? Furthermore, was the Big Bang speculation off base? Join us today as we jump deep into how the James Webb Space Telescope broke the universe. How about we get to the feature and comprehend the trouble and return to when the universe was accepted to have been outlined after the colossal blast? The infant universe began chilling. A couple of million years after the annoying plasma that consumed space settled down, and electrons, protons, and neutrons joined into particles by and large unprejudiced hydrogen. Things were tranquil and faint for a period of questionable term known as the endless faint ages. Then something happened. The vast majority of the material that flew isolated after the immense explosion is made of something we can't see, called dark matter. It has applied areas of strong influence over the universe, particularly at first in the standard picture. Cold dark matter, a term that infers imperceptible or, on the other hand, lazy particles, was flung about the universe carelessly. In specific regions, its scattering was denser, and in these areas it began collapsing into bunches. Apparent matter means particles packed around the bunches of dim matter as the molecules chilled. They at last densified, and the primary stars were conceived. These new wellsprings of radiation recharged the impartial hydrogen that filled the universe during the affirmed time of reionization. Through gravity, larger and more astounding designs created, constructing a tremendous, limitless snare of universes. In the meantime, everything kept on flying separated. The universe is growing quickly. The cosmologist Edwin Hubble figured out during the 1920s that the universe is expanding, and in the late 1990s, his namesake, the Hubble Space Telescope, found proof that the improvement is accelerating. Consider the universe a piece of raisin bread. It begins as a blend of flour, water, yeast, and raisins. When you join these fixings, the yeast starts breathing, and the piece begins to rise. The raisins inside it substitute for frameworks, stretching further separated from each other as the part extends. The Hubble telescope saw that the part is rising much speedier. The raisins are flying separated at a rate that resists their gravitational fascination. This speed increment has all the earmarks of being driven by the stunning energy of room itself, assumed to be dark energy, which is tended to by the Greek letter lambda. Plug values for cold dim matter, normal matter, and radiation into the circumstances of Albert Einstein's general theory of relativity, and you get a model of how the universe creates. This lambda cold dim matter, LCDM, model matches essentially all perceptions of the universe. One method for testing this picture is by checking the uncommonly distant universes out, indistinguishable from recollecting in order to the starting relatively few hundred million years after the Big Bang that started it all. The universe was simpler then, its advancement less complex to investigate against expectations. Stargazers at first endeavored to see the earliest plans of the universe using the Hubble telescope in 1995. Over 10 days, Hubble gotten 342 openings of an unfilled-looking patch of room in the tremendous scoop. Stargazers were stunned by the flood hiding away in the inky dull. Hubble could see great many universes at various distances and groundbreaking stages, reaching out back to a lot sooner times than anyone expected. Hubble would continue to find some genuinely distant universes. In 2016, cosmologists saw its for the most part distant one, called GNZ11, a weak SMCH that they dated to around 400 million years after the Big Bang. This was incredibly right on time for a universe. Anyway, it didn't project out on the LCDM model, in part on the grounds that the world is little with just 1% of the smoothwave's mass, and in part since it remains solitary. The stargazers required a more powerful telescope to see whether GNZ11 was a peculiarity or part of a bigger populace of strange early gigantic frameworks, which could help with deciding whether we are feeling the departure of a central piece of the LCDM recipe. That is the reason the James Webb Space Telescope, or JWST, was imagined lofty as the biggest, most impressive observatory at any point shipped off from Earth. The JWST was worked to adjust how we could interpret the universe, situated 1.5 million kilometers away from normal impedance and chilled close to outright zero by its tennis court-sized sun conceal. The telescope conveys a monster divided reflect and flawlessly touchy instruments that were planned to uncover subtleties of huge sunrises up until now never saw, and that commitment was kept as the main revelations were gotten within the space of weeks after JWST full activities. They were beyond cosmologists' most stunning dreams. It has seen universes very close to the earliest long periods of written history, tried the airs of exoplanets in extraordinary detail, and given staggering new perspectives on universes in our planetary framework. However, it's simply getting all that roll in as Webb's vision ventures into the underlying barely any 100 million years after the immense blast, permitting it to acquire more and better data about newborn child worlds than some other office yet. The underlying question isn't anything not less than our valid comprehension of how the organized universe we know arose out of ahead of schedule stage tumult. Webb's early revelations could change the initial parts of cosmic history, which concerned not just ages and distant universes but also our own presence here in the recognizable smooth way. As JWST researcher Mark McAfee, a senior counselor for space and investigation at the European Space Office, said, "You construct these machines not to affirm the perspective, but to break it. You simply don't have any idea how they will break." Hey, we're beyond cosmologists' most stunning dreams. It has seen universes very close to the earliest long periods of written history, tried the airs of exoplanets in extraordinary detail, and given staggering new perspectives on universes in our planetary framework. However, it's simply getting all that roll in as Webb's vision ventures into the underlying barely any 100 million years after the immense blast, permitting it to acquire more and better data about newborn child worlds than some other office yet. The underlying question isn't anything not less than our valid comprehension of how the organized universe we know arose out of ahead of schedule stage tumult. Webb's early revelations could change the initial parts of cosmic history, which concerned not just ages and distant universes but also our own presence here in the recognizable smooth way. As JWST researcher Mark McAfee, a senior counselor for space and investigation at the European Space Office, said, "You construct these machines not to affirm the perspective, but to break it. You simply don't have any idea how they will break." A type of the Doppler impact is used to gauge the distances of items. This is comparable to sorting out the area of an emergency vehicle in light of a caution. The alert sounds higher in pitch as it draws ever closer and lower as it withdraws. The farther away a cosmic system is, the quicker it creates some distance from us as its light stretches to longer frequencies and seems redder. The degree of this redshift is communicated as Z, where a guaranteed worth of Z tells you how long an item's light likely headed out to contact us. One of the primary papers on JWST information came from Naidu, the MIT cosmologist, and his partners, whose pursuit calculation hailed a system that showed up strangely brilliant and unapproachably far off. Naidu named it Glass Z13, showing its clear distance at a redshift of 13, further away than anything seen before. The system's redshift was subsequently different down to 12.4, and it was renamed Glass Z12. Other cosmologists dealing with various arrangements of JWST perceptions were detailing redshift values from 11 to 20, including one universe called Cheer 1749, or CR2Z71, whose light seems to have left at 13.7 billion years ago, only 220 million years after the enormous detonation, scarcely an eye squint after the start of astronomical time itself. These putative discoveries proposed that the ideal story known as LCDM might be fragmented. Here and there, universes became giant promptly in the early universe. You don't expect seeing massive universes, said Chris Lel, an astrophysicist at the School of Portsmouth in England. For sure, in a survey distributed in November, specialists investigated programmatic experiences of universes represented by the LCDM model and seen that JWST's early brilliant system Zs were organized by size, heavier than the ones that framed all the while in the recreations. A few cosmologists and news sources asserted that JWST was breaking cosmology, yet not everyone was persuaded. One issue is that LCDM expectations aren't generally clear. While dark matter and dark energy are direct, noticeable matter has complex communications and methods of acting, and nobody knows precisely what occurred in the primary years after the huge explosion. Those invigorated early times ought to be approximated in PC reproductions. The other issue is that it's difficult to tell precisely how far away universes really are. In the months following the main papers, the periods of a portion of the alleged high redshift universes have been rethought. Some were downsized to later periods of inestimable advancement due to the refreshed telescope changes. Cheer 1749, for instance, is tracked down in a district of light and dark matter that surrounds the universe, expanding its observations, prompting a reworking of its redshift value down to Z10. Also, the final details show that many of the newborn systems, seen from JWST, might have a tendency toward a reddish tinge or thinness in how much light reaches us, representing a distorted appearance when perceived from our planetary structure. As Webb's vision reveals through more shapes of the earliest cosmology, we may learn that galaxies such as CR2Z71 might be common amidst an unfilled sea, uncovered to have roots deep in the darkness of energy we have yet to reveal. If even a portion of the high redshift, early universes end up being less grand than we think and are connected to more normal galaxies, this is not a bug but a feature of cosmology. The cosmic network makes in fits and starts, the bouncing behavior likely corresponding with a handful of key players in the evolution of spacetime itself. Just like how we assume that life on Earth happened within the first billion years, the same can be expected in the universe. Perhaps we can apply the new astronomy of Webb to look at the universe a few million years back to the impending future. Would we at last check out every universe in its precariousness? As we pivot on discovering the great hidden galaxies, perhaps we will witness the eyes of creation as it unfolds.